Just making sure. Hi. Hi, everybody. Oh. No, you're good. Hi, everybody. Welcome. I'm John Mulcahy. I'm the director of the Carnegie Observatories. Thank you for coming. Yeah, if you don't know. Welcome to our third lecture in our series this season. And tonight is a very familiar face. Many of you will know Jeff Rich, because when I'm not here, he often substitutes for me. Unless he's not available, then Erica substitutes for us. Jeff does our outreach programs at Carnegie, so all sorts of things. I mentioned last time our very intensive trip to Dallas, where we spent a week in schools, and he was part of the program that saw over 15,000 children the week before the eclipse. So that was super exciting. So I don't know why he agreed to give this talk so soon after knowing that big event was coming, but it's been a busy month for Jeff. But tonight you get to hear about his science, which is super exciting, his work on the James Webb, which you're of course hearing tons about. So I think you're going to really enjoy it. I know he has some images that just came out today you're going to see, so that's super exciting. Before I bring Jeff out, though, let me remind you, we want to thank the Huntington for hosting us. We want to thank all of our Carnegie volunteers for helping check everybody in. And we want to thank the Norris Foundation for their support of this series. So it's, they've been supporting this for many, many years, and so we appreciate all their help in putting this on. So with that, I will introduce Jeff. Jeff did his undergraduate degree right here in town at USC before going to the University of Hawaii, where he did his PhD work. He then came to Carnegie as a postdoctoral fellow, and then we hired him as the outreach coordinator just a few years after he started at Carnegie. And as you'll hear about him today, he works a lot on dusty merging galaxies, a super exciting field. So with that, help me welcome Jeff Rich to the stage. Jeff.
Thank you for that nice introduction. Thanks for having me back give a lecture. It's less intimidating to talk about science than to introduce all of our amazing scientists, so I'm excited to just relax and tell you all about some cool galaxies. So I'm going to talk a lot about data that we used from the James Webb Space Telescope, but whenever I give a talk, I like to start from the beginning. So just so we're all on the same page, I'm going to start with, what is a galaxy? You might recognize this very famous galaxy. It's our next door neighbor. We just celebrated the anniversary of this observation last year. But just, the Wikipedia dictionary definition of a galaxy is that it's a bunch of stars, stellar remnants, interstellar gas, dust, and dark matter that's all held together by gravity. Galaxies come in all shapes and sizes. They can be very small, they can be very big. And when you say small or big in astronomy, you have to specify, do you mean lots of stuff, lots of mass, or is it really, really puffed up? So the answer is both. You can have galaxies that are, very tiny and compact but full of stars, or you can have galaxies that are diffuse and only have very few stars. The picture in the middle is a rendering of what the Milky Way might look like. We live in a spiral galaxy. We can't see it from the outside yet. I'm not working on that, but and just for reference, it's a pretty big galaxy, but it's not the biggest galaxy, right? It's a fairly large galaxy, but it's not the biggest thing out there. But why do we study galaxies? I'm an astronomer. I study galaxies because I think they're cool. Scientists are just people who get really excited about a particular topic. I thought galaxies, amongst many other things in astronomy, are really exciting. But one of the things is there are a lot of unanswered questions, and those questions have arisen as we've observed galaxies for over 100 years now. And this is just a couple of famous pictures, the Hubble Ultra Deep Field and the first deep field released by JWST. We've observed, I tried to figure out how many galaxies have we looked at with telescopes, and I couldn't get a good number. We've definitely looked at well over 1 million. And just by looking at those galaxies and measuring the properties of those galaxies, how big are they, what color are they making stars, are they not making stars, we have kind of this picture of a diverse population. And one activity that I like to do when we do outreach with any age is, if you give people a bunch of pictures of galaxies and you ask them to sort those galaxies into different groups, they end up doing something like this. This is a famous early classification system for galaxies that Edwin Hubble created. And just, we're really good at finding patterns and looking for patterns, and just by looking at a bunch of galaxies, we notice some of them tend to be elliptical, some of them tend to be spirally, and then there are a bunch of weird ones off to the side that just got called irregular. But one of the big questions that that arose out of this is, are you going from elliptical to spiral, vice versa? Is there any connection between these galaxies? Do you go from the ones on the left are yellower, redder, to bluer, vice versa? Is this an evolutionary track? It's not, or it might be. So there are some big questions that we're sort of probing when we look at galaxies, and there are lots of different ways to approach them. I highlight a few of them here. One is that we're still trying to understand, just by counting the number of galaxies at a given brightness or a given size. Early on, we didn't seem to be seeing enough really big galaxies or enough really small, faint galaxies. We have some explanations for why we think that might be, and that's something that we're still working on. Another thing we see is that the supermassive black holes at the centers of galaxies seem to know something about the galaxy they're in. They grow with their host galaxy, and we're still figuring out how that worked and how you got those supermassive black holes in the first place. Another thing is we see a lot of galaxies that are done making stars. And we see a lot of galaxies that are making stars, and everything not really in between. So a lot of trying to understand galaxies is poking at how did you end up seeing all these red galaxies that aren't making stars or blue galaxies that are making stars? What are the differences? Why are the differences there? One of the big things that we look at in a galaxy is gas, because gas is the fuel for making stars and the fuel for making those black holes bigger and bigger. If you run out of gas, or if you take gas and throw it out of the galaxy, or if the galaxy's gas is too hot, it can't cool down and condense, you sort of stop growing, you stop making stars, you might stop growing your black hole. So one of the places we look when we look at individual galaxies is what's happening with the gas. Is there gas? How hot is the gas? And this is the first this is a picture from inside the Milky Way. It's a famous picture of a star-forming region in the Milky Way. And this is just a hint that, what you see with HST is spectacular, and you can zoom in and look at the little star-forming knots, and JWST sees things in a different way. It doesn't look the same, right? It looks the same, but it doesn't look the same. So what's the difference? What is JWST doing for us if we want to study galaxies or gas in galaxies? JWST is a space telescope. It's a larger space telescope than the Hubble Space Telescope, but it's not a replacement, it's a complementary telescope. It looks at near and mid-infrared light, where the Hubble Space Telescope looks at primarily ultraviolet visible, and there's a little bit of overlap at the very red end of the visible light spectrum, where JWST can see that same wavelength. But it sees galaxies, it sees stars, it sees whatever you want to study in a very different way than the Hubble Space Telescope did. It also has a much bigger mirror, so if you go back and look at the same things that you did with Hubble, you get a lot more light, you get a lot more information a lot more quickly. So the other great thing about infrared light is, depending on the wavelength, it can pass through dust. So this thing on the left, this Pillars of Creation, is a very dusty star-forming region, and when you look at the left and right, left is, they're both Hubble, but one is infrared and one is visible light. You can see through dust when you look at infrared wavelengths. Another really important thing is that the James Webb Space Telescope is seeing further back. It can see further back in time. It can see distant galaxies much more easily because it's looking at infrared wavelengths, where galaxies in the distant universe their light has been shifted much redder than our eye can see, and James Webb can see those things no problem. I don't study those, but it's doing a lot of really exciting work with distant galaxies. It's also able to see signatures of molecules that are only visible, can only be studied in the infrared. So it allows us to see molecules that are tracers of, say, atmospheric processes and exoplanets. That's something that's really exciting that I don't know very much about, so I'm not going to talk about it. But exoplanets. I threw some extra slides in my talk, so I hope I don't go over too long, but this is brand new this morning. Images from the two on the left are not James Webb. They're to show you how much detail James Webb can see when we go back and look at something that we've already studied quite a bit. So this is the Horsehead Nebula in Orion. It's a cloud of gas that's being lit up by very young stars that were just born. And the image on the right is a really zoomed in little region. This was just released this morning because they just released the paper, studying the Horsehead Nebula in great detail. The images that were taken ranged from near-infrared to mid-infrared, and they used it to study what's happening in that star form, in that region, in that place where stars have just been born, where there's a bunch of gas and dust, in really great detail. The James Webb Space Telescope is able to see the nebula at scales 40 to 400 AU. An AU is an astronomical unit, so the distance from the Earth to the Sun is 1 AU. So you're looking at the dust and gas on scales that are essentially the size of the solar system. That sounds really big, but it's really small. That's really zooming in when you look at distant objects. One of the other things I'm going to talk a lot about tonight is spectroscopy. And this is one of the extremely phenomenal capabilities of JWST. It gets talked about a lot by astronomers because we're seeing some absolutely spectacular data, but you don't often see the data itself in the same way that you see beautiful images taken with JWST, because the data, they're tough to look at. But the physics of what we are studying is encapsulated in a spectrum, and you take that light and split it into a rainbow of infrared colors and measure exactly how much light you're getting at all those different wavelengths. And JWST is really a spectacular telescope in that it has a number of capabilities that span a range of wavelengths, and I'll let you look at this very technical picture for a little while and just take it all in. But just, when JWST's first data drop happened in summer of 2022, I think we had an idea what we thought we might see, and we saw it, and seeing the spectra that the telescope was getting, it left us all in awe. So this is one of two slides where I talk about distant galaxies. JWST is seeing distant galaxies in more detail than we could ever do before. It's seeing galaxies as they were, a few 100 million years up to just 1 billion years after the Big Bang. We're learning a lot very quickly about these really distant galaxies. The record for most distant observed galaxies has been broken and will be broken again by JWST. It seems like we're observing these galaxies, even though we can't observe them in as much detail as nearby galaxies. It allows us to make measurements about how the universe was, how the galaxies were in the early universe, and to test the models that we have for building galaxies early on. And we're running into some interesting results that don't fit with our picture. The Big Bang's not broken, cosmology's not broken. You might see headlines that say that. That's not true. We're just figuring out why we see what we see. But I study really nearby galaxies. And the JWST can look at anything at any distance. And the beautiful image on the upper left is the Tarantula Nebula. That's a star-forming region in the Milky Way galaxy. And you can see a lot of detail if you're interested in studying the physics of what happens to the gas and dust and how it relates to star formation. You can look at things in the Milky Way, but you can step out to nearby galaxies and study them in great detail, and all of this helps us understand those less well-resolved distant galaxy observations that we would have no clue in understanding if we didn't look at all these more nearby things. And I like to look at really bright nearby things. So really easy for the James Webb Space Telescope to see because they're some of the brightest infrared objects in the universe. They're so bright that almost all their light is coming at infrared wavelengths. The amount of infrared light from these galaxies is 100 billion to 1 trillion suns worth of light just at infrared wavelengths. All of this light is basically dust that is being warmed up by really intense star formation. A supermassive black hole that's giving off a lot of energy. I'll talk a little bit about that. And that dust gets warmed up and it re-radiates light at infrared wavelengths. These were discovered by the IRAS satellite in the 1980s. We went and looked at these really bright infrared sources, and many of them were merging galaxies. So not just merging galaxies, but big gas-rich merging galaxies. So take a galaxy like the Milky Way, which is pretty big and forming stars, and take another galaxy like the Milky Way and throw them at each other and see what happens. Some cool stuff happens. We think it's a really transformative process that basically what you're seeing is these two galaxies begin to approach each other. They get close enough that they start to tidally interact. During this process, gas is funneled towards the centers of these galaxies. It feeds the supermassive black hole, which causes a lot of intense radiation in the form of an active galactic nucleus. It also causes a whole bunch of star formation. This doesn't happen all at once. This takes maybe 1 billion years from start to finish, depending on all of your initial parameters. But what you start with might be 2 star-forming galaxies like the Milky Way, and what you end with is something completely different, a big red elliptical galaxy that's no longer making stars. So we think this is a really transformative process. So looking at them in the nearby universe lets us see all the steps in that process in a really detailed way, which I mentioned it takes 1 billion years, so we unfortunately don't get to sit and watch one of these happen and play out and measure how it happens. What we do is we look at as many of them as we can, and we work with theorists who model them, and we compare our observations with their results, and the observations are always correct, and the models sometimes have trouble. So one thing you might have heard before, and we always like to mention when we talk about merging galaxies, is the Milky Way is going to go through this process in a few billion years. Our nearest neighbor, Andromeda, looks like it's on a collision course with us. So some distant astronomer in another galaxy looking at the Milky Way and Andromeda might see a step in that process, and they might see a luminous infrared galaxy, a ULIRG, someday. You don't have to worry about that right now. The other thing, whenever I read about this, it's the Andromeda galaxy and the Milky Way galaxy, and the proposed name for the merged remnant is Milkomeda. We should work on that name. I can think of something better. So I'm going to talk about some of the work we did with early JWST observations of these galaxies. It's work done by a group that I work with called the Great Observatory All-Sky ULIRG Survey. We were lucky enough to be selected to receive early release science data. So these data were taken, some of the data were taken before any data were released to the public, but essentially what we proposed to do was look at just a few galaxies that we had a lot of really good ideas about how they might look with JWST because of existing data. And we said, we think we'll be able to get some interesting results, and we'll be able to test out all of the software and work with the community to get some interesting science, and also make sure all the nuts and bolts of processing the data are going well, because these are so well studied already. And they're very bright, so we know we're going to see something with JWST. The early release science data was focused on these 4 systems. There are a bunch of telephone numbers. They don't have any cool names like Jeff's Galaxy yet. But for folks who study galaxy mergers or luminous infrared galaxies, these are some really interesting objects. And we first got data within a week after everyone saw the first images from JWST. So this was July of almost 2 years ago now. And one thing that happened when JWST data were released is a lot of us went back and looked. We were super excited because we knew we were going to see something, and we had an idea. But we like to illustrate how much better the data are, even for these really, really bright nearby things. This is a galaxy, 2 Zwicky 96. You might recognize the Zwicky name. This is from a catalog Zwicky had of this galaxy is not one galaxy. This is a couple galaxies. Some people think it might be 3 galaxies. The jury's still out. But what we do know is that most of the light in this galaxy is coming out in the form of infrared light. That infrared light is nearly invisible at visible wavelengths. There's no light there in the Hubble Space Telescope image, but there's a ton of light at infrared wavelengths. The previous infrared telescope, the Spitzer Space Telescope, which was an absolutely fabulous telescope, but it only had a mirror that was about this big. We were able to measure all that infrared light using that telescope. This is the image from the Spitzer Space Telescope that we had going into the JWST observations. So all of the infrared light is one big blob. And we think it's from stars, but we're not sure. So when you observed it with JWST, you went from one big blob to a bunch of tiny blobs, which is really exciting. Trust me. It's exciting because it's starting to, well, so number one, we didn't know we had a guess, but we didn't know what we were going to see. What we saw is interesting because even though it resolved some of that big blob into small knots of star formation, we were still left with an incredibly compact, bright point in the middle. And that told us that to the limits of JWST, 70% of the infrared light in this thing is still coming from a cluster that's 500 light years. This is small. This is a small little cluster making stars at a rate 60 times the entire Milky Way galaxy. It's a really intense burst of star formation, and this was the quickest result that we got. The person leading the paper had it done in 2 months, which is fast for us. This is my favorite system because this is the one that I got to study from this initial data, so I'm going to talk a lot about it. But one thing I wanted to do is sort of give a shout out to the people who make these beautiful images for NASA and for ESA, because that is a whole different skill set. When the data come in, they don't look anything like this. When we look at data, I'm going to make you, oh, never mind, you don't have to look at raw data. My program got shut down. When we look at data, it looks nothing like this. This is a combination of many different images taken together. The way that we collect data is through individual filters that block out very specific colors of light. Infrared light, of course, your eye can't see it, but the artists choose specific colors to represent those infrared colors, and they combine multiple images that have to be processed and made to look nice to make this beautiful color image, and do so in a really artistic fashion that conveys something about what's happening in the galaxy scientifically, but also looks really spectacular. And one thing I wanted to highlight is the difference. Again, this is an infrared luminous system. These are two galaxies merging together. The Hubble Space Telescope image on the left, the brightest portion in the JWST image is almost completely extinguished in the HST image. So that green circle, if you didn't notice already, is pointing to the brightest infrared source in the JWST image. We had a hint of where it was going to be from previous data, but we didn't know what we were going to see until we looked at it with JWST. The other really spectacular thing about JWST is it covers a huge range of infrared colors, of infrared wavelengths, from the near infrared to the mid infrared, and those colors of light trace really different processes, so you can do a lot of science even just from images. And you can see, again, without going into too much detail about what you're looking at, the image on the left is near infrared and the image on the right is mid infrared. And you can see where there are similarities, but you can see the difference in what is being traced. The image on the left is mostly going to be old stars or very dust-obscured stars, and the image on the left is going to be star clusters, but also wispy dust and carbon associated with the interstellar medium. And again, to highlight the quality of JWST data compared to our previously available infrared data, we like to put this image next to the Spitzer Space Telescope. So the image on the left was the best image we had at similar wavelengths of infrared light before JWST. And there's a lot of information in that image. We learned a lot from that, but unpacking JWST is a lot. It's a lot. There's a lot there. In fact, most of the time when we're looking at what we did early on was we zoomed way in to these little blobs, these little knots, because that's where the action is happening. In this galaxy, this really spectacular merger of two galaxies, this luminous infrared system, most of the infrared light is coming from these two little blobs. We had a guess that was probably going to be the case from previous data, but we didn't understand their nature. We wanted to know, does this thing have a black hole that's actively accreting. How fast is it growing? Is how fast are stars being made? What's happening behind all that dust that we couldn't see through with the Hubble Space Telescope? One of the early things we learned is that there are a whole bunch of really young star clusters that you just couldn't see with previously available telescopes, and JWST picked those out no problem. We saw all these star clusters. We saw a lot of star clusters we'd already seen, which is great because it allows you to cross-correlate and cross-calibrate, but about 20% of the clusters that were found with JWST weren't observed before. We just couldn't see them. And it turned out those clusters, I'm going to show you, oh, here we go. I'm going to show you the difference between, so the red, you see the red is HST. I'm going to do it again. There we go. So where it's red in that HST image is where we're really digging in and finding a whole bunch of these really young clusters. And I'm going to make you look at a plot. Those clusters were, it turned out, incredibly young. They're only 1 million years old. That's young. That's really young. These are not baby stars. They're very young stars. So it was letting us see these really young clusters for the first time and to sort of get hints at the rates of how fast you make these clusters and how fast you make stars. And some of these clusters are almost as bright as globular clusters. They're really, really intense and tight little clusters. And we're still finding that. That was one galaxy, and it was really interesting, but now we have several more that we want to go and look at, several more that have lots and lots of clusters. We want to understand at what rate these are being created, and at what rate they're being absorbed and assimilated into the galaxy. So that's something we're still learning. But one of the most exciting galaxies that we looked at was this one, NGC 7469. You're all going to remember that. Because we knew that it had an active supermassive black hole, one of these supermassive black holes that has hot gas around it that is shining very brightly. And we knew that around that supermassive black hole there's a ring of star formation. So we knew that from previous observations with Hubble Space Telescope, with radio telescopes. So we were excited to look at it with JWST because even though we knew what was there, we didn't know what we would find with this new telescope that we couldn't see before. One thing that JWST allowed us to do was look in great detail at all those little blue blobs around the supermassive black hole and to measure all their properties to understand what, if any, impact that supermassive black hole is having on star formation. But I want to start talking about spectra because I mentioned this is really the most exciting thing to me about the James Webb Space Telescope. And to do that, I have to show you more data. This is a spectrum from this galaxy that has an active black hole. This spectrum was taken with the Spitzer Space Telescope. The y-axis is just brightness. The x-axis is wavelength of light. So we're looking at mid-infrared wavelengths, 5 microns to 30 microns. If you want to know, that's how wide the wavelength is. And this is all of the light. You take all the light inside that blue rectangle, and you add it up, and you use your spectrograph to measure exactly how much flux or light you're getting at each wavelength. And all of those wiggles and bumps correspond to emission from different atoms, emission from what are called polycyclic aromatic hydrocarbons. It's like the stuff you scrape off of a grill after barbecuing. But out in space. They're hints at the chemistry and physics that are happening in the interstellar medium in this galaxy. And we learned a lot from this Spitzer spectrum about this galaxy. When we pointed JWST at the same galaxy, you get a spectrum from, and if you add up all the light in that red box, you get something that looks like that. The good news is it looks really similar. That might sound boring, but it's not. That means we're doing something right. We see several of the same features. We see similar shapes. We see similar fluxes. Perfect. We know that we're looking with this brand new telescope at something we've looked at before, and we can learn a lot from that. But the exciting science bit is twofold. Number one, JWST has integral field spectrographs. So you don't have to add up all the light in that box. You can pick specific regions or look at just the black hole or look at just that little bit of gas or that little bit of star formation. And one other really big difference is the resolution of the data are so much better, and the intensity. So because of that big mirror and because of these amazing spectrographs that were built, you can see in unprecedented detail features that we had hints of, but we had a really hard time measuring with the Spitzer Space Telescope, and they just pop right out. The little picture there, the red that's an argon, singly ionized argon emission and molecular hydrogen emission. The people who have to work on this data are just excited to see that they can actually get some information where they had to sort of guess before. There's a lot of work to make that nice spectrum. You don't usually see spectra because you would have to sit and label everything and read exactly what you're looking at. It's not as exciting as the beautiful images from JWST, but there's a lot of physics in there. But what we start with is the raw data from the telescope is the thing on the left, and you have to do a lot of work to get that to look like that thing over there. And not only that, there's spectral information and spatial information. So you're getting a map of all these different colors of light that correspond to different features. So you can make a map of different kinds of gas, of different temperatures of gas, of dust, of all kinds of really important things that we want to learn about galaxies. So what you can do, coming back to this galaxy with a big black hole in the middle, is not just look at a picture of the star formation and measure how it's happening, but you can go and extract individual spectra from all of these different places where star formation is happening, and then take a look at all of them. And I'm not going to sit here and go through each one of these, but trust me, there's a lot going on in there. This is really exciting because it allows you to make these really interesting and intricate measurements. And doing that is not easy. We have folks on our team who've been working to develop software who can take that data and throw it into a box and then give you a lot of information about the features that you see there, about the strengths of the different lines caused by molecules or atoms or these dust features, so that you can actually make all those measurements and figure out what the heck you're seeing. This is one of the early results where we saw not just the fact that this thing has a supermassive black hole, but we're able to look at the distribution of the hotter atomic gas, the cooler molecular, the warmish molecular gas, and features that trace not just the black hole and the star formation, but also how the gas is moving. So I'm going to play this video. We'll see if it works. Okay, everybody got that, right? Do it again. As you step through, this is a cube of images at different wavelengths, and they carry information about the velocity of the gas. So you can measure not just what the gas is and the properties of the gas and the dust, but how it's moving around. So we found these really intense, these really highly ionized lines that have these big wings that are caused by gas that's being blown out of this supermassive black hole. And we expected to see that, and one of the early results is that, yes, it's got a supermassive black hole, it's heating the interstellar medium, and we're still picking apart some of the details. So this was just an early sort of test of our observations that a few people worked on, but over the last year or so, other postdocs and grad students have been really digging into the data to look at it in more detail. And a postdoctoral scholar down at UC Irvine, working with someone on our team, spent a lot more time analyzing these data, and she found not just gas that's being blown out by this supermassive black hole, but that we seem to be seeing gas actually flowing in towards the center, which is something we expect to see. So that's good, but actually measuring it is a whole different can of worms. And this is something that she measured for the first time, using these data and modeling and spending a lot of time on it. We like to find these supermassive black holes actively growing because it helps us look at the steps in the process for growing those black holes. So one thing that we knew we were going to see with this galaxy was all of the hallmarks of one of these actively accreting supermassive black holes. There are these features that are emission lines from atoms that have been stripped of electrons because they're exposed to an intense radiation field. We see dust features that are associated again with this active galactic nucleus. All of these features that are hallmarks of AGN that we can then apply when we're searching for those in both distant and nearby galaxies. So to finish, I want to come back to this galaxy, this pair of galaxies, because one thing we did is we spent a couple of months looking at these data and looking at the images, and just from the images, just from looking at the colors of light that JWST gave us, we saw something that we didn't expect. We saw that we didn't have a clear indication that there was any actively feeding supermassive black hole. We had a hint of it, and it wasn't where we expected it to be. We knew this, or we had a guess of this, because this system had been observed a bunch by not space telescopes, but also by ground-based telescopes. So last week, 2 weeks ago, we had a speaker talking about how great radio astronomy is, because it is. So we actually learned a lot. We had some anticipation about what we might see in the system from ground-based radio and millimeter observations taken at the Atacama Large Millimeter Array. So some other scientists had drilled down into the features behind the dust, and they had predicted that there was going to be this spot where we expected to see an actively accreting supermassive black hole. So we went and looked at the JWST data, and we went and grabbed spectra, because the spectra are where we thought we would see signatures of this actively accreting supermassive black hole. We also look at some star formation and some other stuff. But we went and looked at all these spectra, and we went and looked for all those features that you look for, these really highly ionized emission lines. We looked for evidence of dust destruction. We looked for things that we thought would be caused by this black hole, and we didn't see them. We didn't see them where we thought we would see them, and we didn't see them anywhere else. But maybe we did. It was a little weird. So what we did, all of these spectra I have been showing you are taken by an instrument called MIRI. It looks at mid-infrared wavelengths, 5 microns to 25 microns if you want to get specific. And we had observed this galaxy, this pair of galaxies, we'd observed all of these with another instrument called NIRSpec that looks at near-infrared wavelengths. And one of these features that we wanted to look at that's maybe evidence of a supermassive black hole is only seen by this near-infrared instrument. The problem we had is that it turns out calibrating these data is tough. And folks at Space Telescope and at ESA had been working really hard to make the software to be able to allow us to even analyze the data. And there were some kinks early on. But within a couple of months, we had sort of worked them out. So we went back, and we didn't start over, but we went and looked at the near-infrared data for the first time. And we went back and looked at the spot where we thought there would be a black hole. We thought there should be a black hole in the one circled in red. There's not. It looks like it's just a bunch of star formation that's intense and buried and really cool for other reasons. And we looked at that thing circled in yellow. Those two things are the brightest knots in the infrared. One of them we think has to be the nucleus of this galaxy that's very hard to see because it's obscured at visible wavelengths. And when we looked at the near-infrared spectrum, the yellow spectrum had these features that, well, rather it was lacking a feature that traces star formation. So we thought, okay, maybe there's a supermassive black hole there, but we're still trying to understand, based on this one feature at 3.3 microns, you're all going to remember this, it's the 3.3 micron polycyclic aromatic hydrocarbon feature, okay? It's associated with star formation. It's these complex carbon molecules that are in the interstellar medium that are excited by photons, and they cause these features that you see in the infrared. And typically, when you have one of these intense radiation fields caused by an accreting supermassive black hole, these features are diminished or depleted. And that's the only signature we had that there might be a supermassive black hole. and we don't know why we don't see these other features. We think it must have something to do with the geometry, and the cool thing is other folks have come along and looked at these data in a lot more detail. The other reason this 3.3 micron polycyclic aromatic hydrocarbon feature is interesting, right? You're all going to remember this, 3.3 microns polycyclic aromatic hydrocarbon feature, is I mentioned before that, and many of you know this, when you look in the distant universe, light is redshifted. So you're looking at something that was blue is now much redder. So when you're looking at a very distant galaxy with JWST, most of these infrared features, many of the infrared features are shifted so far to the red that you would have to look at them with some other telescope. This 3.3 micron feature we actually see in distant galaxies. And one of the early results from JWST was they took our data, our observations of this feature, or lack of it, and they looked at a very highly redshifted galaxy, so something a couple of billion years after the Big Bang, and they saw evidence of this feature, and they used it to identify where they thought there might be star formation and where they thought there might be a supermassive black hole in one of these very distant galaxies. So when I say we like to look at the nearby ones because we can pick them apart in great detail, take great pains to model the lines very carefully so that when you look at something in the distant universe, you have a hint of what you think you should be seeing. That's the spectrum on the left is the spectrum of the blue is the spectrum of the distant object. And it's smooth and it's not as pretty as our beautiful nearby data. I'm showing you a bunch more squiggles because there's a lot of other stuff that I'm not going to talk about because there's so much information in this single set of data that the next thing to do for other young scientists is to dig into it. And when we published these results in early 2023, a PhD student came along and was really interested in looking at all those little squiggles inside that box. Because it turns out, I didn't know this, which is why it's great to work with other scientists, those squiggles are really interesting. If you zoom in on those squiggles, which is what this PhD student did, they're caused by molecular gas. So she looked in great detail at the carbon monoxide, water, what is C2? Hydrogen cyanide, and I forgot what C2H2 is. Anybody remember? Acetylene. Is it acetylene? Okay. Molecular gas. These are tracers of cool, dense gas, which is really important for tracing star formation. I'm not a chemist. I'm an astronomer. But what she did is really dig into these features and model them very carefully, and started to pick apart why we didn't see some of these other really strong features associated with AGN, and also more evidence that, yeah, it seems like there's an actively accreting supermassive black hole, but the geometry is a little different, and we're trying to piece that apart. And that there's these other signatures that are, tracers of really hot young stars, so the place where we thought there was a supermassive black hole, there's probably not, and we're still trying to figure out why that is. Essentially, it has to do with how the gas and the dust and the radiation are all mixed up and what you get out on the other end. But I say this only to highlight I am still trying to wrap my head around the work that this student did, the student and her mentor, because it's an incredibly detailed analysis of an incredibly rich data set, which tells me all of the other data that we have and that we're getting are going to yield really exciting results. It's just going to take us a little while to analyze all of that data, which is what we're doing next. So I told you about 2.5 of these luminous infrared systems. We observed 4 of them for this early release science. And there are a bunch of other data that are being taken by members of the team that I work with and by other members of the community that will all be public. That we're going to dig into. So instead of looking at individual galaxies, we're going to take some of these ideas and see how do they look across all of these different merging galaxies. And I say that these data are public, so you all are welcome to grab them anytime. They're in a beautiful data archive, but it's a lot of work to get to the analysis portion. And all of this is little hints of what we're going to see, and I'm happy to speculate wildly if you have any questions. So thank you.
Yes, I noticed that you used mid-infrared and near-infrared to image the same exact part of the sky. What different kinds of information are you looking for when you use those two different wavelengths?
There's a lot of different information encoded in there. There's the near-infrared light is going to tell you more about the what's happening with the stars, the stellar populations, the star clusters. It's not directly tracing the dust typically, where the mid-infrared light is going to tell you, you might be able to directly see indications of what's happening with the dust, which is being impacted by stars, or maybe being impacted by a supermassive black hole, or it might be impacted by all the physical processes happening in the galaxy. The cool thing is there's overlap. So the telescope is designed beautifully to allow you to compare things all the way along the way. But there are folks who are really only interested, for instance, in a single feature caused by, say, hydrogen light at a given wavelength. So they might only observe a system in near-infrared or mid-infrared. Or.
Thank you.
We have a question coming in on our YouTube live stream asking if JWST is being used to study brown dwarfs and how that's happening.
Brown dwarfs, wow. It must be. So brown dwarfs are stars that didn't get to be stars. They're not big enough to be a star, but they're bigger than planets. We've been looking at them for a long time now. They are brighter at infrared wavelengths, so JWST, especially those near-infrared wavelengths, would be really good for studying the atmospheric properties of brown dwarfs, which are still being figured out. And they're sort of like cousins to planets. So they're, depending on what we think about planet formation, they're a really rich area of study to understand the processes and atmospheres around really massive planets. There's probably brown dwarfs in there somewhere.
Yeah, so I'm curious, even with like a 6.5 meter mirror, there's more of the sky than you can possibly look at in a short amount of time. So how do you prioritize where to look and who gets to pick?
So the process for selecting who gets to look at what is an annual call for proposals where everybody writes their idea down and anybody is welcome to apply. Panels of experts get together to read chunks of those proposals, usually within their field of study. They work together as groups to sort of rate and review them and pick what they think will be the most exciting science from that set of proposals. And the amount of exciting science proposed far exceeds the amount of time. As you said, we can't look at every single thing. So the data I talked about tonight, they were early release data, so they were meant, the specific call for proposals was in addition to very exciting science that we hoped would come out, something that was cases where we knew we would see something interesting and would be able to calibrate new data from a brand new telescope. Moving forward, once the telescope was working, as soon as there was a first general call for proposals, people understood the capabilities of the telescope better and could judge, okay, now that we know it's working, what will be the best thing to look at? And it's tough. I think it's less than 10%. Do you know the call last time? It's roughly 10% of proposals get through. And that's the case for the Hubble Space Telescope as well.
I have a very basic question. Of the galaxies that you're studying, do they all have the same properties? And do you ever find a property in your results that come back that you don't know?
So they're all generally, the ones that we're looking at are all generally galaxy mergers, or they're in the process of merging. They're about to merge, or they're done merging, mostly. Some of them are not, and they're very bright in the infrared for other reasons. In this case, what we have been finding that surprised us is some of the chemistry and some of the properties of the radiation field, so the details of the physics of what's happening in the interstellar medium is not what we expected. But it's the nuts and bolts of figuring out, is it the modeling of the data that's incorrect? Is it the spectrum? Do we just not understand the data well enough? Is it that I don't think we've made a mistake in our analysis, but you always worry about that. So where we thought we would see a supermassive black hole based on all of the evidence up to JWST in this one merging system, we didn't see it. And we're trying to figure out why that is. We think it's just because the data weren't good enough before, and that's great. That's fine.
Yeah, I have a very basic question about twinkling. So when you see those rays coming out, I always thought when I'm looking at the sky that those are caused by the atmosphere, but then infrared, we're not looking through dust, we're seeing through the dust. And so is it still, it's getting a little bit of twinkle, or is that just the artist's rendering, or what's causing the twinkle?
No, that's a really good question, and almost every press release that has images like this takes care to explain what's happening there. So those lines are called diffraction spikes. Anytime there's a very bright object, it could be a star. In this case, it's one of those really bright clusters. The light picks up information from the telescope on its journey from the mirror to the secondary mirror through the instrumentation. So the shapes are caused by diffraction caused by the telescope itself. Wow. Now, when you're looking at light coming through the atmosphere, you're getting similar processes. But so it's not quite the same as twinkling, but its physics is the same. But that pattern is something that we have to take into account. That pattern, you can account for that by taking an extra set of images that are not as blown out as that. In fact, we did that in this case. This is a beautiful artist's rendition that shows those diffraction spikes. They're really bad for analyzing the data because they get in the way and obscure things. So there's a different image that we took that doesn't have those diffraction spikes so that we can drill down and look right at what's happening in the core. So what's really funny is everyone on that we work with, they kept not complaining, but they kept wondering, why does everyone keep asking about the spikes? Doesn't everybody know what those are? No, people don't know what those are. And it's really good. That's a great question because and the other interesting thing is there are astronomers who can look at an image and say, just based on that pattern, I know exactly which telescope it came from because each telescope will have a unique pattern based on the secondary mirror, for instance.
Wow. Cool. Thank you.
Just a quick question. Given the massive amounts of data you guys are analyzing and the massive scope of the canvas, are you able to use AI in your analysis?
I think the short answer is yes. There are lots of people, there are whole conferences happening already discussing what are the best ways to apply machine learning to current analyses that would help move things forward in a productive way. In the case of the nuts and bolts of fitting all those little features, for instance, that's something that if you can tune something that you trust well enough to not fail catastrophically, that's a place where it would be useful and has been applied. So yeah, short answer is yes, but we're still figuring it out.
When you look back at the early universe and try to look at the different species of atomic or molecular species, do you see the evolution in time basically conforming to our models, or there's any surprises there?
So far, yes. This is where I'm still learning because the molecular gas that JWST is looking at requires a great deal of care in modeling all those little wiggles, and the changes that the work that was done in analyzing just that one system was trying to come up with an explanation that fits the physics of the transitions that generate those states. So yes, we see things we expect, but it took a lot of time to pick apart what we thought we were seeing. That's very vague, but I'm waving my hands because I work with people who are experts at doing that fitting, to those really complex features. And then it's spitting out information that looks pretty much like we expected. But what's really cool is instead of where before you would have a single point, on a plot for an entire galaxy that told you something about how hot the dust is or whether the black hole is reprocessing gas and dust. We now have, you can have 10 or 50 or 100 pieces of information from across the galaxy that tell you something about not just the average properties, but the physical properties as they change, as the environment changes.
So what about the elemental composition?
That's something, yes, that's something that I want to do but haven't done yet with the data. So that's because in the infrared you're seeing different because of all the dust, you're seeing a different piece of the interstellar medium than you do at visible wavelengths. So that's something that is on my to-do list, on our to-do list, that I want to do but haven't done yet. I had aspirations of doing it before this talk, but that was silly. Maybe over the summer.
Thank you.
Yeah, we have another question from the live stream. Someone is asking, is JWST able to see everything in the universe? And if not, what more do we need to be able to see what we're not currently seeing?
It can't see everything. No, this is an amazing new telescope with a mirror that is bigger than any mirror put in space that is looking outward, and it's looking at wavelengths that we couldn't see before. So it's seeing galaxies that we couldn't see. But certainly there are planets around other stars. There are galaxies that it just won't be able to see either because the mirror is not big enough, or in some cases there are physical processes that give off a lot more light at visible wavelengths or ultraviolet wavelengths. So there's a whole complement of proposed ideas for other telescopes that complement JWST that look at, say, physics of a planetary atmosphere or gas in another galaxy that you don't get from JWST. In the same way that JWST is complementary to the Hubble Space Telescope. The capabilities are similar but different enough that they're answering questions that one telescope couldn't answer and vice versa. I guess a telescope as big as the universe. It's what do you want to see? And it depends on what you're interested in looking at.
Okay, thank you. My question is, you talked about using models to try to predict what you would observe when those galaxies you just showed us merged. Are those models computer simulations, mathematical models? What's the nature of that?
So there are people who simulate merging galaxies, who try to use what we think we know about gravity and matter and dark matter, and the physical processes, the star formation, the movement of gas, how gas turns into stars, and you put all that in a computer simulation, throw two galaxies at each other, and in bulk look at the properties of those simulations and compare it to what we think we observe. There are people who drill down on the radiative processes, so the radiation field, how it changes as it goes through different kinds of gas, goes through different temperatures of gas and dust, and try to recreate what we think we would observe based on that, and then compare that to, say, a given dust feature.
Okay, so you're applying multiple models from different, okay.
Yeah, it depends on the question you're asking. Again, I'm really interested in things like understanding how much star formation is happening, how fast the black hole is growing, or what the chemical abundances are in the interstellar medium. And so you would apply different sort of models to those questions depending on what you're interested in.
Got it.
And I forgot to mention, when we're talking about what we can see with the next telescopes, that you're also limited by mirror size. The next really big telescopes are going to be built on the ground. So the Giant Magellan Telescope, for instance, that will be able to see things that JWST can't see, even though it's not looking at mid-infrared wavelengths. So I'm going to give a shout out to the future ground-based telescopes that are going to see things that we're getting hints from JWST that we want to go back and look with this really giant mirror on the ground and really see something that we can't see with JWST. We'll come back in a few years and talk about that. Thank you.
And a reminder that our last lecture is in 2 weeks, and those tickets are available starting tomorrow morning at 10 a.m. So don't miss out. We'll see you in 2 weeks. Thanks, everybody. Thanks, Jeff.
Thank you.